In this question, we have a book being pulled up an inclined plane by a horizontal force Fa of magnitude 19 newtons. The mass of the book is 3.18 and the distance the book slides up the plane or the ramp is given as 0.98 meters. We're also told that the ramp is frictionless and the angle of inclination is given by 30 degrees. Question A requires us to find the normal force that acts on the book. And then question B requires us to find the speed of the book at the end of the displacement with the given conditions stated there. So, first thing first, we have to understand what the question is asking us to find and how we can relate it to laws of physics that we know. The first thing we want to find is the work done on the book. We all know that work done is equal to the force acting on an object multiplied by the distance the object travels in the direction of the force. So that's the key point. This distance has to be in the direction of the force F. So if the direction of travel is up the ramp, that is D, we want to find the force that is in that same direction. So let's draw this inclined plane again. I'm gonna have a rough sketch of this inclined plane. So we have 30 degrees, and let's say this is our book up the inclined plane at any given point. We would have two forces acting on it. Fa, the horizontal force, and a vertical force, which is the weight, Wt, which is mass times gravity. Okay, now we need to find the component of these two forces that are parallel or acting in the direction of the plane. Okay, if you look at, let's start with one. If you look at Fa, it is acting horizontal, in the horizontal direction. That means the angle between the plane and that force is also 30 degrees, right? So with that being said, we would have two components, right? One acting at a 90 degree to the plane and the other acting in the same direction or parallel to the plane but upward. I'm gonna call that one X, but before that I need to make some adjustment to my screen. I'm gonna move this so you can see it clearly. Sorry, my video is a little bit okay. So it's clearer now. So now Fa has two components, one that is perpendicular to the plane and the other that is parallel to the plane. The one parallel to the plane is what we're interested in, and I'm gonna assume that the x-axis is along the plane, so I'm gonna call that component FAX. Now, if I bring out that triangle that is formed by the plane, or FAX, the perpendicular components, which we would call FAY, and FA itself, this is 30 degree, this is FA. We find out that the relationship between FA and FAX is cosine 30. So we have cosine 30 degrees is equal to FAX, which is adjacent side over the hypotenuse, FA. Hence, we can solve for FA, X is equal to FA cosine 30 degree. I'm gonna leave that as that here. And then we do the same thing for the weight of the object. So I'm gonna go back to the original diagram we have, which is this, the one in black. The weight of the object will also have two components. One that is perpendicular to the plane and one that is parallel to the plane. Now this angle in here will be 30 degree, and then solving this or bringing out this triangle, we have MG here, then we have the perpendicular component, which I'm gonna call WT, weight in the y direction. This is 30 degree, and then the one parallel, but in this case you see it is parallel to the plane but going in the downward direction. We'll call this weight X. Taking a look at this right angle triangle, because it's a right angle triangle, I don't mind drawing, it's not accurate enough, but it's a right angle triangle, and then we see that the relationship between MG and weight in the X direction is given by sine 30. So we have sine 30 is equal to what? WTX over MG. So we can find WTX equal to MG sine 30. So these are the two components of forces acting along the direction of travel. So we need to find the resultant of these two forces. Now, the question says the book slides the distance d. D is in the upward direction, so we have F net, which is in the direction of travel, will be FAX minus WTX. Why that is because FAX is going upward and WTX is downward, and if FAX is the larger of the two, then the object actually traveled the upward direction. So what it means is that FAX won the fight for direction. So now we'll have this will give us FA cosine 30 minus WTX. I already have the value for WTX in terms of MG, so gonna be mg sine 30, I mean. So we're gonna plug in the values. Remember, FAX is 19 Newton, theta is 30, or we have that plugged in already, and the mass is 3.18. So I'm gonna just write it on this side. FA is 19 Newton, M is 3.18 kg. So we have everything we need to compute the numerical value for this, right? So we have 19 cosine 30 minus 3.18 times 9.81 gravity sine 30, right? I'm gonna press that out. So we have what? 19 cosine 30 minus this gives a net force of 0.8566 to 4 decimal places. So F net is this. Now we can find the work done on the object, right? On the book, I mean. So work done, like we said, is force times distance. Now distance in direction, always in direction, always in direction of F. So we have 0.8566 times what is the value of the distance traveled. It is 0.98 meter. Let me just put it here. So D is 0.98 meter. So we're gonna plug in here 0.98, and now we can find the value of the work done on the object. 0.8566 times. This gives a value of 0.839 joules. Now going back, that is the first question actually. So this is the net force. The net work. Let's see. The net work done on the book by FA. Yeah, that's that. The second question, B, asks us to find the speed of the book at the end of the displacement, given that the kinetic energy at the start of the displacement is 0. So B, we want to find final speed, right? I'm just gonna call that V, right? Now there are some assumptions that are already in place which are not necessarily important, like initial velocity, which I'll call V0, is 0, but since we're not using the equation of motion, which we can use, this is irrelevant. Now KE, kinetic energy, is given by 1/2 mv squared, right? Now we need to find the final kinetic energy. The final kinetic energy, I'll call KE final, is equal to KE initial, this is an I, plus work done. So work done, the work done is done on the book, not done by the book. So it's a plus. If it's done by the book, it's gonna be a minus here. So remember, we're told that the initial kinetic energy is 0. So simply put, we have our final kinetic energy as just the work done, which we just calculated in part A of this question. So now we can simply equate kinetic energy to work done. So therefore we have that 1 over 2 mv squared, which is after the displacement, because this is the energy or the work done on the object after the displacement, is equal to 0.839. Hence we can solve for v. V squared will be 2, multiply both sides by 2, 839, this is 8, and then divided by m. Hence v is equal to square root of 2 into 0.839 over m. We have m as 3.18, remember? So by plugging all these values in, we have the value of m in, we have 0.839 over 3.18. I'm pressing it out. It gives us 0.727 meters per second approximately. So in conclusion, we have been able to find the net work done by FA and the speed at the end of the displacement. So net work done B, oh, sorry about that. Question B, net work done, we got it at 0. I can't remember, 0.39, sorry, 839, 0.839, that doesn't sound right. And then, this is A, and then B, we found the final speed. The speed at the end of displacement, 0.727 meters per second. And this marks the end of the question. Thank you for watching, and I hope this helps.